Hi there, welcome to another episode of Electrical Engineering Challenge. Thanks to all who have subscribed and shared, and please hit the bell icon, click subscribe if you like the video. That way we can keep growing. We're over 100 now. I really appreciate everyone who's subscribed so far. Hope you find these interesting. And if you have any questions about any type of challenge, or if you're having some issues or want to see something, just go and make a comment down below and I'll take a look at it and see if I can make an episode on it. So now let's go ahead and get on with the design today. So today we are straying away from the usual challenge, and we're going to be diving into USB-C protocols. I wasn't sure about how I'm going to make a challenge for this, so I decided to just do the instructional minus the challenge. I'm a CE by trade, well, by college, and most of my career I've been doing hardware design, double E. That's why there's been a lot of hardware challenges here, but I do have firmware knowledge. And so with this one, because we're going to be talking about USB-C, rather than trying to do some hardware aspect of it, I would go through the explanation of what USB-C is, how we can use it, and how we can use firmware in order to get the information that we need. So a few things to note when working with USB-C is they have items called PDOs. These are power delivery objects or contracts. These are the things that the brick would supply, the source would supply to the sink, right? And they can be either fixed output supplies or they can be a PPS, a programmable power supply, which we'll see a little bit later. And so the USB-C system has two aspects to it. It has a downward facing port, right, or a DFP, and a sink, which is the UFP or the upward facing port. So you have either the source, the DFP, or you have the sink, which is the UFP. For the basics of it, a standard brick that you buy off of Amazon is the source, and this is the thing that will be delivering power. And something like your phone or a device that wants to utilize the power coming from the brick, this would be considered the sink or the upward facing port, and this would be the object receiving the power. So this is the USB-C brick that we'll be using as our DFP, as our source. And I couldn't find any specs on this Amazon website, and I couldn't take a picture of it because the print's really small. But has 5 options on it that are listed on the device, which is 5 volts at 3 amps, or 9 volts at 3 amps, 12 volts at 3 amps, 15 volts at 3 amps, or 20 volts at 3.25 amps to give us the 65 watt output. So it comes with all of these fixed PDOs that we'd be able to choose from when we start the communication protocol. For our sync, we will be using this Diodes Inc. dev board for an AP33772 controller. And so our USB-C input will come here, and our output voltage will be this Vout load connector here in the upper right. And we will be communicating through the I2C bus here, right, through those 4 pins, talking to an Arduino Mega. And so you can see the basic outline of what's going on the block diagram here, at the bottom. And so you have the USB-C input, and you have the controller here, and this MCU that we're connected through I2C. That will be our Arduino Mega. And so you can see basically what's going to happen is this controller, it will communicate over the CC1, CC2 lines back to the controller. Actually, let me just blow that up a little bit for you. So we can see that it's going to communicate back to the USB-C with the CC1, CC2 lines here. It'll do all the translating for us. And then based on that communication protocol, it will then turn these 2 NMOSs on to allow power to go to the load. And we will be determining that contract or that PDO that we want using the Arduino Mega. So the USB-C connector is reversible and has multiple connections. So we have the V-bus and the ground, right here, V-bus and ground for power delivery. And we have C1 and C2 here. This is for the USB-C protocol and communications. We have D plus and D minus. This is for the old school USB 2.0, the micro USB, things like that. And we have SBU1 and SBU2. These ones are special use case. These are the only two non-reversible pinouts, and these are for lower speed sideband communications for certain things if it's necessary. So for this one, all we really need is the V bus in the ground and the C1 and the CC1 and the CC2 pins to be able to do the communication and deliver the power. So to harness the power of the USB-C brick, we do need to communicate with it. And like I said, there's a lot of more people out there smarter than me that deal with this. So we're just going to use the chip. There's multiple ones out there. You don't have to specifically use this one. TI has one, the TPS5730, which is pretty reasonably priced and does what you need. I'm using the Diodes Inc. AP33772. Both of these are controllers that will do all the hard work for us. We just need to communicate over I2C to get it to do the work. So here's my Arduino code. If you want me to go into more details on the firmware implementation, let me know in the comments down below. I'm just going to gloss over a lot of it because it's just it's firmware, right? It's code. But we'll see the gist of exactly how to implement the main aspects of it. But you can kind of see here, I made myself some I2C device objects here, and I got the AP33772 object so that I can just basically firmware, right? Making the classes and whatnot. So in the Arduino code itself, if we go down to the setup, basically all I'm doing is establishing the device, which is the AP33772, and its I2C address is this 0x51. I have device detected being 0. That just, like I said, we got to detect the device, so I'm setting it to false at this moment. It also has some interrupts on it, the controller. The chip has some outputs that it does, some interrupts. So I went ahead and attached an interrupt there. I'm not using them for this, but it's things like over temperature faults, over current faults, over voltage faults, anything that causes the chip to go into a frenzy, it'll send an interrupt, and then I can get some feedback over the I2C lines. And I go ahead and initialize that AP33772. And all that's really doing is initializing the I2C bus. It's because I have nothing connected yet, or I don't know if anything's connected yet. So I'm not really initializing this per se, but what I'm really doing is I'm just establishing the I2C communication protocol. Now in the loop, basically what I'm going to do first is all I'm going to be doing is waiting for a device. All I'm going to be doing is waiting for a device. And when the device is connected, let me go and clear that for later. So it's going to wait for the device. And so long as the device isn't detected, then it's just going to do this infinite loop, waiting for something to be detected. And how do I determine if it's detected? Well, the chip has a status byte that I can read. And so that's all I'm looking for. If the device gets connected, it's the AP33772. It's attached to that address, that 0x51. Then I should be able to get something back, right? Some status, some feedback, which would tell me that, hey, something is connected to that address. So let me go ahead and try to do some stuff. And so that's all I'm doing right here. If status comes back as greater than or equal to 0, then I've got a device on there. This function, it returns a -1, a negative number, if there's no feedback, if the I2C bus times out. So I have it time out after like 200 milliseconds or something. I have some timeout in there, so it'll give if I don't see anything when I'm asking for the status bit, I just send a negative number and it tells me that still nothing's connected. So it'll just loop in here, and then I just give a small delay so I'm not cycling this thing like a madman. So give a 10 millisecond delay, and it'll just keep doing that. Once it does detect it, then I'll go ahead and device detected. I'm just delaying here 1 second. No real reason, just give everything time to boot up, right? Because it got plugged in, I got my status thing, just it should be booted up right now, but I'm just giving it a second so there's no issues, right? And then I go ahead and set this mask. This is for that interrupt pin, right? So I can check for status. Well, sorry, this isn't for the interrupt pin. This is actually for status. This mask also has to deal with the interrupt, but I'm not setting any of those interrupts. I'm just checking for PDO successes, right? And then what I'm going to go ahead and do is just going to request the contracts, right? So if I click on this one right here and I go to the definition of request contracts, you can see there, I'm just going to print out how many PDOs there are. So I'm going to get this is one of the function calls. I can just get the PDO count, and then I'm going to get the contracts, and then I'm going to go ahead and print the contracts. And all the contracts are going to do to print out is basically, remember there's two of them. We have a fixed PDO and we have a PPS, right? This PDO, a PDO. And so depending on if it's a fixed PDO or a PPS, will determine what the output is. But basically it's just going to say fixed, what's the voltage that's available, and what's the current. And these multipliers right here, because it's going to send me a byte, and that byte is in 50 millivolt increments. And same with the current. The current's coming back to me in a byte form, and each bit is equal to 10 milliamps. So it'll print out the voltage and the current for the contracts available in the fixed. And if it's a PPS, if the thing has a PPS, then it'll print out the minimum voltage, it'll print out the maximum voltage, and the max current. And if it's a PPS and you select it, you can actually request anything within that range, and it will deliver that. So I'm going to go ahead and use the webcam so we can actually see what's going on with the devices. You can see here I've got my Arduino Mega, and the only thing I've connected to this thing is my I2C and the ground, which are going back to the dev board over here. And so, and then the pin 2, that's my interrupt pin right there. And so I don't have a really good setup for electronics for display yet. Sorry about the images. But so we have our AP, this is the dev kit for the AP33772. And of course we have our USB-C input over here. And then over here we have the output, which I'm just connecting right here. You can see the probes, and they are connecting up to the DMM. And so you can see right there, it's set to 0 volts because one, if you look down here, I don't have anything plugged in. And so of course there's going to be 0 volts on the output of that. So let's go ahead and take the brick and we will go ahead and plug it in. So we'll go ahead and plug it in. And so I don't know if it's coming out, but you can see the LED. So we've got power. There we go. We still got 0 volts because again, it's just powered on, but nothing's happening yet. You can see as soon as I plugged it in on the serial monitor, we had the device detected. And when we read it, we immediately saw that we have 6 PDOs available, which is what we were expecting. Actually, we were expecting 5. Remember, when I wrote it out, the document that was given with it only listed fixed PDOs. And so you can see here, we got the 5 reported fixed PDOs that we were expecting, right? The 5 volts at 3 amps, 9 at 3, 12 at 3, 15 at 3, and 20 at 3.25 amps. And this thing also comes with a PPS option, right? So we can choose anything from 3.3 volts to 11 volts at 3 amps max. So we can go ahead and set what we want through that PPS option on this brick if we wanted to. For the most part though, we could probably just stick with we're wanting to use the fixed ones. So then how do we actually get to choose this? Well, if we scroll down in the code a little bit, you can kind of see I'm just looking for, again, I'm checking for the status just to make sure that it's always connected. The reason why is because if I unplug it, say I just unplug it, you can see there the device got disconnected, right? So it goes back into the loop and it then waits for a device. So let me go ahead and plug it back in. Device detected again, and we get our feedback again. So we can easily see it getting connected, disconnected, and we're able to read it. And that's from constantly checking for this status to make sure that we got something. So what do we do now that we know what contracts are available? Well, we take a look at them and find out which one it is that we want. Normally you would do this programmatically, like if you want a 12-volt system, or you want the 15, or you want the 20. And so you'll go ahead and request what you want. For this demonstration, I just gave numbers, and these numbers correlate to what PDO contract we would like to engage with. And I just did it on a serial output, so I can just select 1, 2, 3, 4, 5, or 6, and then it'll go ahead and set it. I didn't set anything in there for the PPS, so I'm only going to work with the fixed ones on this. But you can see here, I'm going to go ahead and request the 5-volt output. So I just click 1, and then what does it do? It go ahead and sets that contract to the one that we want. And then it go ahead and gets the status. And then what it does then is this isn't the voltage and the current, but I can get the voltage and the current of the bus. Remember I said that I could give some feedback. So this is the actual voltage and the current that's on the system. Since I don't have anything connected to it, it's not reading back as any current, but you can see even though I'm asking for 5 volts, right now it's got a float voltage of 5.12 volts, right? Even though it's like a 5-volt 3 amp, because there's no load on it, I'm getting a little bit higher reading than what's expected. And I can go ahead and change it. This is highly dynamic, so we can change it. Let's say we want the 12 volt. So if we look over in our chart, 1, 2, 3, 4, 5, 6, right? 3 is the 12 volt. So if I go ahead and write 3 there, boom, it go ahead and changes it to the voltage now on the output is 12 volts. And you can see it up here on the DMM. You can see that the voltage on the output went to 12 volts. And again, if I just go ahead and do 5, that'll bring it up to 20 volts. And I can just go through that all I want, plug it in, unplug it. And so this is a very dynamic system, and we can change it as needed if we wanted to. So why is it that we want to do this? Well, a lot of times we work with 5 volts, but if we just want to make a project and we don't want to, and we want more voltage to lower current, or maybe we just need to drive something higher, like we have a 12-volt relay, or we got a 12-volt servo motor or something like that, and we just need more voltage, we can just run our whole system off of this USBC brick by asking for the voltage that we want. So most times back in the day, you only had 5 volts to work with. Now we have an ability to use multiple voltages, right? Like 5 volt, 9 volt, 12 volt, 20 volt from this brick you see. And 3 amps is a lot of power. So we can do many more things now, and we have a lot more capability to be able to use it once we learn how we can use the tools to be able to get that voltage to us. So that's all I have for you today. It was just a quick little demonstration on USB-C protocol and how to kind of use a controller with an Arduino to be able to take a look at the registers, read them back, and how the thing operates. And like I said, if you want to go into details, I can go into more details with the firmware on the next video. If you're interested, comment down below, and I'll go through a procedure of how I took a look at the data sheet and how I read it and how I set up my firmware so that I could be able to do the things that I need to do. But that's all for today. Thanks for watching, and I hope you enjoyed the video. And thanks to all who have subscribed and shared, and I'll see you next time.